Hello, this is day 2 of chapter 16, which is static electricity and electric fields. Now day 2 is going to take what we learned in day 1 and it's going to add a whole new dimension. In day 1 you only had 2 charges, a positive and a negative, or a positive and a positive, and you see how they interacted with each other, how much force they attracted towards each other or repelled each other. Now that was day 1. In day 2 we're going to take it another level. We're going to go ahead and now make it 2-dimensional. So now we'll be dealing with 3 particles, and they're not going to be a straight line. Now they're going to be away from each other as shown in the picture. Now, what this will require is some knowledge from previous chapters that is coming back. For example, sine, cosine, tangent, law of sines, and even law of cosines. Alright, so let's go ahead and get to work on our first problem. First problem is sample problem B out of page 567. In this problem, the book already comes with the picture. So this picture is drawn out of the book. And then they describe the following. Consider 3 point charges. There, and there. Q1 is 6 times 10 to the negative 9 coulombs. Q2 is negative 2 times 10 to the negative 9 coulombs. And Q3 is 5 times 10 to the negative 9 coulombs. Find the magnitude and direction of the resultant force on Q3. Alright, so we'll be looking at Q2 is going to put force on it. Notice we have a positive and a negative, so it's going to be an attractive force. So Q2 is going to pull Q3 that way. And we'll also be looking at Q1 and Q3. Notice that they're both positive, so it's going to repel. So it's going to go in that direction. So the force is going to be in that vector, and it's going to be in that direction as well, because positive and negatives, opposite charges, they attract. Alright, so that is what we'll be looking at. We're also going to need to figure out some angles in this triangle. Now, in the picture, they do let us know that it is a right triangle. It is a 3, 4, 5 right triangle. Great. So we need that information as well. So let's go ahead and get started. First of all, I need to figure out the force between 2 and 3. So I'm going to put force 2, 3, so that I label it so I know which one I'm talking about. So between 2 and 3, it's equal to coulombs constant, which is 9 times 10 to the 9 newtons times meters squared over coulomb squared. Multiply times the 2 charges, 2 times 10 to the negative 9, and 5 times 10 to the negative 9 coulombs. All of it is divided by the distance between them, which is 4 meters. And that is squared. Alright, so that will be the force between charge number 2 and charge number 3. Put it in the calculator, 9 times 10 to the 9 times 2 times 10 to the negative 9 times 5 times 10 to the negative 9 divided by 4 meters squared, which is 16, equals 5.6 times 10 to the negative 9, and that is newtons. Alright, next part, we need to figure out now what is the force between charge number 1 and charge number 3. So force between 1, 3. So label it so I know which one I'm referring to. Alright, so it's going to look very similar. Here is the constant. Multiply times the charge. The charge is going to be 6 times 10 to the negative 9 coulombs. For the charge for our third charge is 5 times 10 to the negative 9. And all of it divided by 5 meters squared. And the 5 is the distance between charge 1 and charge number 3. Alright, so in our calculator, 9 times 10 to the negative 9 times 6 times 10 to the negative 9 times 5 times 10 to the negative 9 equals 2.7 times 10 to the negative 9 divided by 5 squared. That gives us 1.8 times 10 to the negative 8. I'm going to write it slightly different. Instead of 1.8 times 10 to the negative 8, I'm going to slide over the decimal one to the right, giving me 10.8 times 10 to the negative 9. So I moved over decimal ones to the right. That's why instead of negative 8, it says negative 9. Why would I do that? Well, it allows me to easily compare. You see how they're both 10 to the negative 9, 10 to the negative 9. So I can easily see that this one is nearly twice as big as that one. So it makes for an easy comparison. Alright, so we got the force between 2 and 3, 1 and 3. So this is our first of many parts to come to solve this problem. Alright, so next I need to know this angle. So we know the force going this way, we know the force going that way, we just got them. Alright, I need that angle right there. So I'm going to go ahead and solve for that. Let's change color for that. So for that angle, I'm going to label it theta. Alright, so what is the value of it? Alright, so I'm going to go ahead and use opposite over hypotenuse, so that is sine. So sine of theta, it's equal to opposite over hypotenuse, 3 over 5. Alright, so if I want the angle, I'm going to use the inverse sine. So the angle theta is equal to the inverse sine of opposite over hypotenuse, so 3 over 5. So the answer for that is, I'm going to round it off to 37 degrees. That is this angle right here. It is 37 degrees. Alright, so we got all the forces, we got the angle that we needed. Now we need to go ahead and draw another vector diagram to show how these forces interact with each other. Okay, so I'm going to draw that right here. And let's draw our first force between 2 and 3. That's going to be 5.6. So I'm going to go ahead and get my ruler, make it about 5.6. That's going to be kind of small. I'm going to double that. So it's about 11, a little bit over 11. Alright, so that's our first vector. We have our force that is 5.6 times 10 to negative 9 newtons going that way. And our next vector is going that way, in that direction, at 37 degrees Celsius. What's that vector? It is 1 and 3. Between 1 and 3, it is 10.8 times 10 to the negative 9. So that's going to be 10.8. And about that angle, so roughly about that. So the end of one arrow, that's where the other arrow begins. And this one, it is 10.8 times 10 to the negative 9 newtons. The angle right there, that angle is actually the same one as 37 degrees. Why is that? Because these two are congruent from your math class. So they are the same. So there you go. Those two are congruent angles. Now the question that you're being asked to solve in this problem is, alright, so where's that arrow going? Alright, so what is the vector? When you combine two vectors, you could refer to that as a resultant. So what is our resultant? So we're going to draw that arrow right here. And that is what we're solving for, the length of it. On top of that, they're going to want the angle. Which angle? That one right there. Because they ask, what is the magnitude, which is the value, the length of that arrow, and the direction. So which direction is it traveling at? That's what we're looking for in this problem. So also we're looking for that angle right there. Alright, so solving this problem next is that length. We have a theorem that we've used. That is law of cosines, a law that we use, I should say. Alright, see we have side, angle, side. So therefore that will be our resultant. So we're going to go ahead and use law of cosines to solve for that problem right there. Okay, so law of cosines, it is r squared is equal to a squared plus b squared minus 2 times a times b times cosine of theta, which is 37. Alright, so let's plug in all these values. R squared is equals a squared. Either one of these could be a, it's irrelevant. I'm going to go with the top one. 10.8 times 10 to the negative 9 squared plus b 5.6 times 10 to the negative 9 squared minus 2a and b, 10.8 times 10 to the negative 9 times b, 5.6 times 10 to the negative 9 times cosine of theta, which is 37 degrees. Alright, so that is our law of sines, law of cosines. I was solving for the resultant, which will give us that distance right there. Alright, so let's go ahead and solve. First thing I'm going to go ahead and do is I'm going to go ahead and take care of this side. Square both of these, then add them to each other. So 10.8 times 10 to the negative 9 squared plus 5.6 times 10 to the negative 9 squared. That gives me 1.48 times 10 to the negative 16. Over on this side, I'm going to go ahead and multiply cosine of 37 times all those values. So it's going to be cosine 37 times 10.8 times 10 to the negative 9 times 5.6 times 10 to the negative 9 times 2 gives me 9.66 times 10 to the negative 17. Alright, I'm going to go ahead and do the subtraction. For 1.48 times 10 to the negative 16 minus our answer gives us 5.14 times 10 to the negative 17. Notice I still haven't gotten rid of the square, and I do want to, so I'm going to square root. And that's going to give us a resultant. So square root of the answer equals 7.1 times 10 to the negative 9. 7.17 times 10 to the negative 9. And that is our resultant. So that's 1 over 2 answers. So this is our length right here. 7.17 times 10 to the negative 9 newtons. Alright, so we got our first answer out of 2. Our next question is, what is that right there, the angle that's traveling at? Alright, so how do we go about solving for that? Well, it's a bit of a tough problem. This is what I would go ahead and do as far as what I think would be the easiest would be to extend this triangle so we can have a right triangle right here. We have this angle and we have that side. So we can use it to figure out what is this side right here. I'm going to label that one y. And then you see that distance right there, I'm going to label that one x. So let's go ahead and get to work on that. I don't think I need the x. Let's just solve for the y. Alright, so we have here angle opposite over hypotenuse. We do have that. So what's opposite over hypotenuse? That's sine. Alright, so it would be sine of 37 is equal to opposite or the hypotenuse, 10.8 times 10 to the negative 9. So we'll move this one over here, giving us 10.8 times 10 to the negative 9 times sine of 37. That equals that distance y right there. Great. Now we have it. Let's go ahead and solve. So let's see, sine of 37 multiplied times 10.8 times 10 to the negative 9 gives me 6.5 times 10 to the negative 9. 6.5 times 10 to the negative 9. Alright, so that's our answer for y right here. That's how long that side is. 6.5 times 10 to the negative 9. Alright, now notice this angle we have opposite over hypotenuse. I'm running a little bit out of space. I'm going to erase some stuff here. I think I'm going to go ahead and erase law of cosines. I want to point out this inner triangle. We're still trying to get this angle here for this inner triangle, so we know that resultant, what angle is traveling at. So we have theta equals, we have the opposite and we have the hypotenuse. So it will look like this. Sine of theta is equal to opposite 6.5 times 10 to the negative 9 over the hypotenuse 7.17 times 10 to the negative 9. Of course, I would go ahead and get the inverse sine of that. And this divided by that, what does that give us? Let's see. 6.5 times 10 to the negative 9 divided by 7.17 times 10 to the negative 9 equals 0.906. That's this number divided by that. That gives us that answer. And then I do the inverse sine, because I moved it over here. Inverse sine of 0.906 gives us the angle 65 degrees. So the question, find the magnitude. The magnitude was 7.17 times 10 to the negative 9. Find the direction. The direction is at 65 degrees above the horizontal. So that would be your answer for sample problem B. Excellent problem because it brings together the new stuff we're learning for charges and the attraction between charges, plus it pairs it up with a lot of the work we did with law of cosine we did in earlier chapters. So it's a great problem. Alright, our next problem is going to be practice problem number 1 out of page 568. In this problem, they go ahead and they tell you have 3-point charges, Q1, Q2, and Q3. They lie along the x-axis. X is 0, X is 3, and X is 5 centimeters respectively. So that's 1, 2, and 3. And I already changed this. Values were in centimeters, I changed them to meters. So from the origin, Q2 is at 0.03 meters and Q3 is at 0.05 meters. Then they ask you to calculate the magnitude and direction of the electric force on each of the 3 points if the charges are 6 microcoulombs, positive 1.5 microcoulombs, and negative 2.0 microcoulombs. I also went ahead and took the liberty of changing them from microcoulombs to just coulombs, just to save us a little bit of time. Alright, so our first objective is going to be to figure out what is the force between 1 and 2, between 2 and 3, and between 1 and 3. So that's going to be our first step, figure out the force between each one of them. So I'm going to begin the force between 1, 2. So 1, 2, between that and that. Let's see. What is that? It is the charge, the constant, Coulomb's constant, 9 times 10 to the 9, newtons times meters per second squared, multiplied times the charges for each one. It's going to be 6 times 10 to the negative 6, and 1.5 times 10 to the negative 6 coulombs. All of it divided by the distance in between them, which is 0.03 meters, and that is squared. Alright, so we're going to solve for that. Next, I need to solve for the force between 2 and 3. So I'm going to put force 2, 3, so that I know which one I'm talking about. Force between 2 and 3 is going to be the same constant. It is a constant, it does not change. Multiplied times their charges. It's going to be 1.5 times 10 to the negative 6 and 2.0 times 10 to the negative 6. And all of it divided by the distance in between them. The distance between them is, well, if this is 0.05 and that's 0.03, then that has to be 0.02. Now get the answer for that in a bit. And then the final one we need to go ahead and search for is the force between 1 and 3. Force between 1, 3, it's equal to constant multiply times the charges, 6 and 2. And the whole thing divided by the distance between them, which is 0.05. Alright, so next we go ahead and put these into our calculators to get the value. And let's see, we got 9 times 10 to the 9 times 6 times 10 to the negative 6 multiplied times 1.5 times 10 to the negative 6 divided by 0.03 squared gives us 90 newtons. Next one, 9 times 10 to the negative 9 times 1.5 times 10 to the negative 6 times 2 times 10 to the negative 6 divided by 0.02 squared gives us, I'm going to round it up slightly to 68 newtons. For the force between 1 and 3, let's see, we're going to put 1 times 10 to the 9 times 6 times 10 to the negative 6 multiplied times 2 times 10 to the negative 6 divided by 0.05 squared. Alright, our answer, we're going to round it up slightly to just 43 newtons. Alright, so now what will happen is, let's see, for our very first one, we're going to go ahead and have a force between 1 and 2. Notice how they're both positive, so the force is repulsive. It's going to push Q1 to the left hand side. So over here I put the net force for number 1 is going to be negative 90 because it is 90, the force between 1 and 2, and because it's being repelled going that way I put negative. Now, what else is acting on it? Force between 1 and 3. Now notice that's positive and that is negative, so therefore it's an attractive force. So between 1 and 3 is an attractive force of 43, so it's going to be pulled toward the right of 43. So I put positive because positive is to the right. Put it together, so our net force is negative 47. What does that mean? It means that the overall net force, Q1 is going to the left with a force of 47 newtons. Now the answer is for all three of them. So let's solve for the net force for the second charge. Alright, so what is the charges of acting on it? There's two of them, Q1 and Q3. So notice that both of these guys are positive. So they're repelling. So that's going to push Q2 to the right. So between 1 and 2 is going to go to the right with 90. I'm going to put positive 90 because number 2 is getting pushed away from Q1. And notice between 2 and 3 they're opposite charges, positive and negative. That means that it's also attractive to the right. So that's to the right is positive. So between 2 and 3, here's the force plus 68 newtons to the right. So 90 plus 58 will give you 158 newtons positive. That means that Q2 is going to the right. And finally, the net force for 3. Alright, our third charge between 1 and 3, they are positive and negative, so they are attractive. So it's going to go to the left. Q3 is going to go to the left because it's attracted to Q1. By how much? Between 1 and 3 is going to be a negative 43 because it's going to the left. It's being attracted. And it's also being attracted to positive and negative to Q2, so it's going to go also to the left, so I'm going to label it as negative. The force between 2 and 3, so that's minus 68. So that's going to go ahead and give us 43 and 68. Put them together. It is negative 111 newtons to the left. Alright, so that is the force, the net force experienced by each one of these charges. That concludes practice problem number 1 out of page 568. Up next is practice problem number 2 out of page 568 of your textbook. In this problem they tell you as the following. It says 4 charged particles are placed at the place so that, start over. Up next is practice problem number 2 out of page 568. In this problem they tell you the following. 4 charged particles are placed so that each particle is at the corner of a square. The sides of each square are 15 centimeters. The charges are at the upper left corner is 3 microcoulombs. The charges at the upper right corner is negative 6 microcoulombs. The charge at the lower left corner is negative 2.4 microcoulombs. And then the charge at the lower right corner is negative 9 microcoulombs. So what they're going to ask you to do is A, find the net electric force on the very first one. And then after that they're going to ask you for the other corners of the triangle. For this problem I'm only going to solve the A and let you guys use B and C as practice problems. So let's go ahead and get to work on A. Notice I have the drawing here already, and I changed the distance instead of 15 centimeters to they're already meters. I'm also going to need this diagonal distance between 1 and 3 because those two charges are exerting a force on each other, and the answer for that is 0.21. How I found that is, first of all, this is a square, so therefore it's a right angle, so it's that one, so it's that one, and it's that one as well. And I use Pythagorean theorem to solve for it. A squared plus b squared equals c squared. So that's how I got the 0.21. Here are the charges. Now, how much force do they exert on each other? That is what this problem is asking for. All right, so let's get started. The force between charge 1 and 2. So I'm going to go ahead and label it here. Force between 1, 2 is, let's see, the constant, Coulomb's constant, and 9 times 10 to the 9 newtons times meter squared over Coulomb squared. Multiply times the charges, which are 3 times 10 to the negative 6 coulombs, times 6 times 10 to the negative 6 coulombs, over their distance, which is 0.15 meters squared. Alright, so that is our first one. Let's put in the calculator. 9 times 10 to the 9 times 3 times 10 to the negative 6. Multiply times 6 times 10 to the negative 6. Divided by 0.15 squared. Gives us 7.2 newtons. That is the force between 1 and 2. Next is the force between 1 and 3. So I label it 1, 3, so that's between 1 and 3. It's going to look very similar, where we have the same constant, and we're still using charge number 1, so it's going to be same value. And what we're changing is charge number 3, that is 9 times 10 to the negative 6, and all of it divided by the distance between 1 and 3, which is 0.21 meters, and that is squared. So the answer for that is 9 times 10 to the negative 9 times 3 times 10 to the negative 6 times 9 times 10 to the negative 6 divided by 0.21 squared. The answer is 5.5 newtons. That's the force between 1 and 3. Our last one is going to be the force between 1 and 4. So I'm going to put force 1, 4. So you see that, 1, 4. Alright, and that one, again, very similar. We're going to start with the constant. 9 times 10 to the negative 9. Multiply times the charge of number 1, 3 times 10 to the negative 6. Multiply times the charge of our second one, of Q4, 2.4 times 10 to the negative 6. And all of it divided by the distance between 1 and 4, which is 0.15. And that is squared. I'm going to put that in the calculator. And it gives us 2.9 newtons. Alright, so that's all the forces experienced by charge number 1. Up next, we got to go ahead and draw the vector diagram. Now this vector diagram is going to have 3 arrows. So it's going to be slightly complicated. Alright, so our first arrow is going to go ahead and start between 1 and 2. Notice that they are positive and negative. They are opposite charges, so therefore they are attract. So I'm going to draw an arrow going towards the right because Q1 is being pulled towards Q2. How long should I make it? It should be 7 inches. That's going to be kind of small. Let me double that just so that it's easier to see. So I'm going to put roughly about 14 inches to the right. So that is 7.2 newtons. Our next force is between, let's do this one. It's a little easier to work with. It's going to be, no, let's just go in order. 1 and 3. Between 1 and 3, notice it's at a 45-degree angle. I know that because it's half of this angle, which is 90, so it's at 45 degrees. And it's going to go, let's see, positive and negative, opposite charges. So Q1 is getting pulled down in that direction. Alright, Q1 is getting pulled down, so I'm going to go in this direction at 45-degree angles. And let's see, about 5.5, so that's 11 inches. Alright, and our last one, it's between 1 and 4. Notice again, positive, negative. Everyone is negative, so it's going to pull on Q1 straight down. How much? 2.9. So, let me go ahead and draw that. So there you have it. Notice that this one and that are perpendicular. Perpendicular, the 7.2 and the 2.9. So the question is, what is this value? Big question mark right there. So what is the net force on charge 1? It is going in that direction, so what is it? Alright, cool. That's our problem. Let's go ahead and get to work on it. Alright, so for this problem, I need this. Alright, I do have a right triangle, but I don't have this piece, I have that piece, but I do have enough pieces to figure out the whole length. I'm going to rewrite this one. It is 5.5 newtons. Alright, that's my hypotenuse. And I do know that that is a 45-degree angle right here. Alright, why do I know that? Because remember, it was originally a square, so that is a 45-degree angle there. Alright, so is that one. So we can use that to figure out what is this length. And they'll be the same length because it is 45 and 45, making it an isosceles triangle. Alright, so these two are going to be the same length, that and that. Great. So, let's go ahead and work that part out. Now, let's see. I want this length. I have that angle. I have that angle. Let's go with this one first. Opposite over hypotenuse. So I have sine 45 is equal to opposite. I'm going to call this guy y. Opposite over hypotenuse. The hypotenuse is 5.5. So I'm going to multiply by 5.5 on both sides. Again, 5.5 is times sine of 45 is equal to the length of y. And y equals sine of 45 times 5.5. It's equal to 3.9. So this distance from here to there is 3.9 newtons. Because it is an isosceles triangle, that's also 3.9 newtons. Alright, that's a great bit that will allow us to come closer to the answer. So now if I were to ask you, so what's the length of this whole side? From here to there, then you say, well, geez, it's just that number, 7.2 from here to there, plus that number, 3.9. So 3.9 plus 7.2 gives us 11.1. That's from here to there. Now, same question on this side. What's this whole length? Okay, from here to there, it's going to be 2.9 plus 3.9. 6.8 newtons. Now can you give me that right there? Sure, that will be Pythagorean theorem because it's a right triangle. A squared plus b squared equals c squared. Alright, so that's going to be 11.1 squared plus 6.8 squared. And then I get the square root of that answer. It gives me 13.0. And that is the answer for practice problem number 2 out of page 682. Now that we have derived the formula, all we have to do now is plug in the values in here and solve, and that's going to go ahead and give us our answer. So let's go ahead and do that. So D, it's equal to 2 multiplied times the square root of Q2. So that is 6 times 10 to the negative 6, square root of that, divided by the square root of Q1 plus the square root of Q2. So square root of Q1, 1.5 times 10 to the negative 5, plus 6 times 10 to the negative 6. Alright, so we plug them into the calculator, and we get 6 times 10 to the negative 6, square root of that answer. That gives me 2 times 2.45 times 10 to the negative 3. On the denominator, square root of 1.5 times 10 to the negative 5 times, plus square root of 6 times 10 to the negative 6. Alright, that's going to go ahead and give me 6.32 times 10 to the negative 3. So now I'm going to go ahead and divide both of these, and that will give me my final answer. 2.45 times 10 to the negative 3 times 2 divided by my answer gives me 0.77 meters. That is the value of D. So Q2 should be at the distance between Q2 and Q3 should be 0.77. Alright, so that's between 2 and 3. What about the distance between 3 and 1? Well, it would be 2 minus 0.77. So 2 minus our answer will give me 1.23. That's the distance between Q3 and Q1. Alright, so that is sample problem C out of page 569. Up next is practice problem number 1 out of page 570 of your textbook. In this problem, they say the following. A charge of 2 times 10 to the negative 9 coulombs is placed at the origin. So there you have it. Another charge of 4 times 10 to the negative 9 coulombs is placed 1.5 meters from the origin. So there you have it. Find the point between these two charges where a charge of 3 times 10 to the negative 9 coulombs should be placed so that the net electrical force on it is 0. Now they give us a value of it, 3 times 10 to the negative 9, but we don't need it. It will get canceled out, so it's irrelevant. So the question is, at some point here in between, we're going to go ahead and put that third charge. I'm going to put Q3 somewhere in between Q1 and Q2 so that it's negative, it's going to get pulled to the left by Q1, it's going to get pulled to the right by Q2. Where can we put it so that the value is 0, the net force is 0? Alright, so we're going to use a very similar strategies to what we used in the previous problem to solve this problem. I'm going to go ahead and say the distance from Q1 to that third charge, we're going to label it as D, and it's unknown, so we just put the symbol for D. That means that the distance between the charge and Q2, we're going to label it as 1.5 minus D. Alright, it is 1.5, subtract the D, that gives us that. Alright, so those are important values. Now, again, the force from the left was equal to the force from the right, so they equal each other. So, what is the force from the left side between Q1 and Q3? Well, let's put the formula for it. It's going to be the constant, Coulomb's constant, multiplied times Q1 times Q3, divided by the distance between them, D squared. On the other side, what is the force between Q3 and Q2? It must be the same. That's why I have the equal sign. Is going to be QC, Q3 multiplied times Q2, divided by this distance, which is 1.5 minus D, and that whole thing is squared. Alright, now we can go ahead and simplify this again. What is the same on both sides? You say, well, QC, the constant is the same for both, as well as Q3. I mentioned earlier, We don't need to know that Q3 is 3 times 10 to the negative 9. It's going to get canceled out because it's the same on both sides. So after that, we're left behind with this. Q1 over D2, D squared, it's equal to Q2 over 1.5 minus D, and the whole thing is squared. Alright, our next step is to isolate that D. We're going to use similar steps. I'm going to cross multiply that times that. That's going to go ahead and give us D squared times Q2. It's equal to, cross multiply both of these, 1.5 minus D squared times Q1. Alright, our next step is to begin simplifying. So we're going to go ahead and get rid of all those squares by square rooting. So we're going to get left with this. Square root of D squared is just D times square root of Q2. It's equal to square root of 1.5 minus D squared is just 1.5 minus D. Get rid of the square because you square root it. And on this side we have square root of Q1. Alright, so after square rooting, so we can get rid of the squares, we're going to go ahead and distribute. We're going to distribute the square root of Q1 to 1.5 minus D. So, just bring this side down, and that's going to give us 1.5 multiplied times square root of Q1 minus D multiplied times square root of Q1. Now we're going to go ahead and collect like terms. Both of these have a D in the front, so we're going to move it over because that's a negative. It's going to become positive. So we have D times Q2. It's equal to, plus D times square root of Q1 equals 1.5 times the square root of Q1. Now we're going to go ahead and get the D's and pull them out, giving us square root of Q2 plus square root of Q1 in parentheses times D. So we factor that out. Equals 1.5 multiplied times the square root of Q1. We're going to get this whole thing in parentheses and move it down here so we can have the D isolated. So it's going to give us D, it's equal to 1.5 times square root of Q1 over square root of Q2 plus square root of Q1. Alright, so that is going to be our equation that we derived. From there we can go ahead and just plug in the numbers for Q1 and Q2. There's Q1, Q2, plug them in, and we have our formula. So let me go ahead and rewrite the derived formula. The distance in between them, Q multiplied times square root of Q1 over square root of Q2 plus square root of Q1. Alright, substitute the values in. 1.5 multiplied times the square root of Q1. Q1 is 2 times 10 to the negative 9. 2 times 10 to the negative 9 over Q2 plus Q1. Q2 is square root of 4 times 10 to the negative 9 plus square root of 2 times 10 to the negative 9. Put that into your calculator. We'll take it step by step. On the numerator, we're going to put 2 times 10 to the negative 9. And we're going to square root that. Multiply times 1.5. So it's going to go ahead and give us 6.71 times 10 to the negative 5. On the denominator, we're going to put square root of 4 times 10 to the negative 9 plus square root of 2 times 10 to the negative 9. That gives us 1.08 times 10 to the negative 4. And then just divide both of these, and there is our distance between Q1 and Q3. The answer is 0.62 meters. That is D. So the distance between both of these, from here to there, it is 0.62 meters. So there's your answer. Alright, now this formula would derive, what exactly is this? That will be like our total length from one charge to the other. So maybe you can make a more general formula, just put L right here, and maybe we can use this and not have to derive it again, so we can go ahead and solve for the problem without having to derive it again. Our next problem is very much the same thing, so that's why I wanted to hold on to the formula. In this one, practice problem number 2, they tell you guys, you have a charge Q1 is negative 5 times 10 to the 9, and a charge of Q2 is negative 2 times 10 to the negative 9. They're separated by a distance of 40 centimeters, so that's our length in between them. Find the equilibrium position for a third charge of 15 times 10 to the negative 9, which again, we don't need that value. We can go ahead and figure it out without that value. Alright, so I'm going to go ahead and erase this one. But I want to hold on to that formula so that way we don't have to rederive it for this particular problem. Alright, so what changed? For this problem, our charges changed. So I'm going to go ahead and let's see. For the first one, it is negative 5 times 10 to the negative 9. And for Q2 is going to be 2 times 10 to the negative 9 coulombs. Alright, so we got our charges. And what is our total length in between them? It's going to be 40 centimeters. But we need that in meters, so we're going to divide it by 100. So it's going to be 0.4 meters. So if this is 0.4 meters, that's the total length, and that's D. So what's this one? It is 0.4 meters minus D. Alright, so there we have it. That's our setup. Let's plug it into this formula. So the length is going to be 0.4 meters. So it will look like this. D equals 0.4 meters. Multiply times the square root of Q1. Q1 is, we're going to drop the negative because we don't want any imaginary numbers. Square root of 5 times 10 to the negative 9. On the denominator, Q2, it is 2 times 10 to the negative 9. Square root that. And plus square root of Q1, which is 5 times 10 to the negative 9. Alright, so that's how you would modify this problem. So for practice problem number 2. And we'll plug it into the calculator one more time and give us our answer. So it's going to be square root of 5 times 10 to the negative 9 times 0.4. Our numerator is 2.82 times 10 to the negative 5. Our denominator is square root of 2 times 10 to the negative 9 plus square root of 5 times 10 to the negative 9 equals 1.15 times 10 to the negative 4. Finally, just divide both of these, and that is our answer. 2.82 times 10 to the negative 5 divided by 1.15 times 10 to the negative 4. And that gives us our answer of 0.25 meters for this one. So we were able to use this formula and skip the derivation as we did in the previous problem. Alright, so that is the answer for practice problem number 2. The next one and last one is practice problem number 3. On this one, it says an electron is released from above the Earth's surface. A second electron directly below exerts just enough of an electric force on the first electron to cancel out its gravitational force on it. Find the distance between the two electrons. Alright. This problem is similar, but not quite. Not quite the same. Alright, so we're going to go ahead and derive a formula to solve for this one. What is the distance between the two electrons? Unfortunately, I'm not sure if that will work. Maybe I can give it a chance later. We'll try it. Alright, so for this problem, let's see, we got one electron is on top, and it's negative. They have one electron on the bottom, and it's also negative. negative and a negative, they repel, they push each other away. So the electric force is separating them. But there is gravity pulling down on this electron, so gravitational force is pulling them towards each other. So at what distance do they just stay there because the electrical force and the gravitational force match? Alright, so that's what they want to know. Alright, so now we got to derive a formula for this. So let's get started. For this one's going to be the force of gravity is equal to the force from the electrons pulling on each other, or in this case repelling each other. Alright, so force of gravity is going to be mass times gravity. And the force of the electron is going to be the constant times the charge of one times the charge of the other. But notice that they're both electrons have the same charge. Divided by the distance between them, squared. And that's what we're solving for. Alright, so we're going to rearrange this a little bit. Move the d over here, so I'm going to multiply it times d squared. Alright, and that takes care of that. And I'm also going to divide by mass times gravity. So what do we end up with? D squared is equal to kc times, remember this are the two same charges, so I'm just going to put q squared over m times g. To get rid of the square, you square root, so I'm going to square root on this side, that makes it go away. And what I do to one side, I have to do to the other, and there you have it. Alright, so now we can go ahead and start plugging in values and solving. Alright, so d is going to be the constant, 9 times 10 to the 9 newtons times meters squared over coulomb squared. Q, the charge of an electron, that was given to us in a previous slide. And here we go. Alright, so the charge of an electron is 1.6 times 10 to the negative 19. So I'm going to put that 1.6 times 10 to the negative 19 coulombs. And we're going to square that because there's two electrons. I'm going to divide by the mass of the electron. Alright, so it's going to be rounded off slightly, 1.11 times 10 to the negative 31. That's the mass of the electron on top. We don't care about the electron on the bottom. And gravity, 9.8 meters per second squared. This whole thing is square rooted. So we're going to go step by step. So we're not going to use this other formula. Again, I always advise my students not to do it all in one step. Alright, 9 times 10 to the 9 times 1.6 times 10 to the negative 19 squared gives me, I'm going to continue up here, 2.3 times 10 to the negative 28. That's our numerator. Our denominator is 9.11 times 10 to the negative 31. Multiply times 9.8. Gives me 8.9 times 10 to the negative 30. And this whole thing is square rooted. So now we're going to go ahead and divide. 2.3 times 10 to the negative 28 divided by our answer. Gives me 25.7. Finally, square root of that. 5.1 meters. That will be the distance between our two electrons. Alright folks, so that brings us all the way to the end of this section. And as always, practice makes perfect. So chapter 16, day 2 is completed. Practice, I would assign homework 38, page 582, number 18 and 19 of your textbook. Alright, good luck with those.